Good day. In previous chapters, we have explored the properties of gases and the liquids, both pure liquids and the solutions. In this chapter, we discuss different types of solids and how the properties of the solid state are related to the atomic and the molecular structures of the solid state. Solids may be composed of pure substances or mixtures, compounds, or elements. The classification of a solid will depend on the nature of the substance and how the atoms or molecules are arranged with respect to one another, and the nature of the forces holding particles together in the solid state. The crystalline solids are characterized by the ordered arrays of atoms, ions, and molecules. Amorphous solids have a more random, disordered arrangement of particles. Most metallic materials form crystalline solids in which the atoms are held together by metallic bonds. Nonmetals crystallize as molecular solids in which the molecules are held together by the weaker intermolecular forces, as we discussed in Chapter 10. Atomic solids are formed by weak attraction between noble gas atoms. Covalent network solids are formed by covalent bonds among nonmetal atoms in an extended array. Ionic compounds form crystalline solids in which the ions are held together by ionic bonds. In general, molecular solids exhibit lower melting points consistent with the weaker intermolecular forces compared to ionic or metallic solids. Metallic solids tend to be malleable, ionic solids tend to be brittle. Let's look at a few examples of different types of solids. In metallic crystalline solids, like silver, metal atoms are arranged in an ordered pattern. In an ionic crystalline solid, like table salt NaCl, the anions and cations occupy alternating positions in an ordered array. Notice in the table salt crystalline structure, you do not see a molecule like NaCl. In a molecular crystalline solid, like water, H2O, all the atoms are covalently bonded in a tetrahedral configuration. For a tetrahedral configuration, you also need hydrogen bonds. Note, when we talked about the tetrahedral shape, we are talking about the electron geometry of H2O. The molecular geometry for H2O is bent shape. In an amorphous solid, like glass, the silicon oxygen bond are more randomly arranged. When metals are heated to their melting point and allowed to cool slowly, the atoms arrange themselves in highly ordered arrays called a crystal lattice. The crystal lattices formed by metals and other crystalline solids can be categorized by the way the particles are arranged with respect to one another, or the crystal structure. We define the unit cell of a crystalline solid as the basic repeating unit for the particles in the three-dimensional ordered array. We can identify the stacking pattern as either hexagonal closest packing, which has an AB, AB, AB stacking repeating pattern, or cubic closest packing, which exhibits an ABC, ABC, ABC repeating pattern. If we look at the hexagonal closest packing, we see that the unit cell, can be represented as a hexagon. particles at each of the 6 corners of one hexagon are stacked on top of particles at the corners of another hexagon. In addition, particles are also located on the top and the bottom faces of the hexagonal prism. Finally, there are 3 particles completely contained within the middle layer of the prism, filled in the voids between the top and the bottom of the hexagonal layers. In contrast, the face-centered cubic unit cell is an example of cubic closest packing unit cell. The cubic unit cell is characterized by particles occupying the 8 corners of a cube. In the face-centered cubic cell, there are also particles that are located on the 6 faces of the cube. That's the name face-centered cubic. Note that in the face-centered cubic cell, the particles occupying the corners don't touch, but the particles along the diagonal of any face will be in contact, as you see in this picture. The simplest example of cubic unit cell is the simple cubic unit cell. In the simple cubic unit cell, there are particles located on each of the 8 corners and none on the faces or within the body of the unit cell. This structure is the least efficient in terms of packing. Perhaps the only example among metals is radioactive polonium. The final cubic cell is the body-centered unit cell. In the body-centered cell, there are 8 particles located on the 8 corners of the cubic cell, and 1 particle at the center of the unit cell. All group 1 metals like sodium, potassium, cesium, and the many transition metals exhibit body-centered unit cell structure. And in this periodic table, we have indicated the unit cells of metals and the metalloids in the periodic table. Note that in group 1, the metals and the several transition metals exhibit body-centered as indicated as green, etc. Group 2 and the rest of the transition metals exhibit either face-centered, cubic, or hexagonal unit cells, which are the most efficient stacking patterns. Please note that some of the group 14 or group 4A elements exhibit a diamond-like structure, which we will discuss in a later section. In this table, we have summarized the characteristics of the basic unit cells, including the number of nearest neighbors and packing efficiency. The number of nearest neighbors is determined by the number of particles that are immediately adjacent, although most not necessarily touching. For example, consider the simple cubic. A particle on any corner would have 6 nearest neighbors, each located on either side along the x, y, and z axis that define the cell dimensions. The number of nearest neighbors sometimes is also called the coordination number. For a body-centered cubic, the particle centered within the body of the unit cell would have 8 nearest neighbors. The particles occupying the 8 corners in proximity to the center of the cell will be surrounding the center atom. In the face-centered cubic, the hexagonal unit cell, the number of nearest neighbors is 12. Please note that the hexagonal closest packing and the face-centered cubic are the most efficient in the packing efficiency. The most efficient packing will have a packing efficiency of 74%, with the simple cubic as the least efficient packing with a packing efficiency of only 52%. The density of a crystalline material can be calculated by the mass of the unit cell divided by the volume of the unit cell, because the unit cell will repeat itself and make the bulk material. The dimensions of each of the cubic unit cells can be calculated based on the number of atoms that are touching each other. For simple cubic, the atoms on the edge, they are touching each other. As you can see, all the edge atoms are touching each other. For the body-centered cubic, the diagonal atoms are touching each other. Diagonal atoms are touching each other. For the body-centered cubic, the atoms in the interior diagonal, the center atom and one atom in one corner and the other one in the other corner, they are touching each other. So, according to the Pythagorean theorem, we can derive the relationship between the edge length L, edge length, and the atomic radius. The volume of the unit cell will be the edge length cubed. In addition to the cell volume, we need to know the mass of particles in the cell volume, which is related to the atomic mass and the number of atoms or particles in the unit cell. We can calculate the number of atoms in each of the unit cell by identifying the locations of the atom in the cell and identifying how many adjacent cells share a part of that particular atom. Consider, for example, the atom at the corner of a cubic unit cell as shown in this figure. Any given corner of the cubic unit cell is actually shared by 8 cells that meet at the point. In other words, for corner atoms, only 1/8 of the atom is contained within the given unit cell. In contrast, the atom on one of the 6 faces, if it's the face atom, half of the atom is inside this cubic. For this reason, for the face-centered cubic unit cell, we have 8 corners. For these 8 corners, each corner contributes 1/8. All the corner atoms will give 1/8 times 8 corner. This is 1 atom. We also have 6 face-centered atoms. Each face atom contributes a half. So 6 of them will give you 3 atoms. So in total, it's 1 plus 3 atoms. So you have 4 total atoms inside the unit cell for the face-centered cubic. Similarly, it can easily be seen that an atom in the body of the body-centered unit cell is completely contained within that cell. Atoms located along the edge of a cell is shared by 4 unit cells. So for this reason, the edge atoms only contributes 1/4 of an atom inside the unit cell. So all edge atoms will contribute 1/4 for each one times the total of 12 edge atoms, and the edge atoms will contribute 3 total atoms inside the unit cell. For the simple cubic unit cell, there are 8 corners. Each corner contributes 1/8, so it has a total of 1 atom inside the unit cell. For body-centered cubic, there are 8 corners, each contributing 1/8. And you also have a center atom. The center atom is totally inside the unit cell. So you have a total of 2 atoms for each body-centered cubic unit. For face-centered cubic unit, 8 corners each contributes 1/8 times 8 corners. And you also have 6 faces. Each has a face-centered atom. Each face-centered atom contributes a half, so times the 6 faces, you will have a total of 4 atoms for each unit cell. The characteristics of cubic unit cells are summarized in these two tables here. The contributions of the number of atoms in the unit cell for each location, the face, body, and corner atoms are summarized over here. Unit cell dimensions and the relationships to atomic radius are included in this table, along with the number of atoms per unit cell. Let's work on an example. Tantalum crystallizes with a body-centered cubic unit cell. Its unit cell has an edge length of 330 picometer. Calculate the radius in the picometers of the tantalum atoms. We are given the unit cell, body-centered cubic, and the edge length L is 330.3 picometer. We need to calculate the radius. The tantalum atoms do not touch along the unit cell edges or along any face diagonal, but they do touch along the body diagonals. So the body center with one corner and the opposite corner, they are touching each other. So for this reason, we already know the radius and the edge length relationship. So we can substitute the edge length into the formula. So radius R will be the edge length times square root of 3 over 4. This gives you 143.0 picometer. Let's switch gear and talk about different alloys. We define an alloy as a blend of a host metal with one or more other elements, which may or may not be metals. The properties of the alloy may be significantly different than the properties of the host metal in the pure state. For example, pure gold is extremely soft, but when mixed with other metals like nickel, tin, copper, it becomes hard enough to be used in jewelry, etc. Alloys can be classified in terms of how the added substances are distributed, as discussed in the previous chapter dealing with mixtures. Homogeneous alloys are solid solutions in which added elements are uniformly distributed at the atomic or molecular level. Two examples of a homogeneous alloy are brass, which is a mixture of copper and zinc, and bronze, which is a mixture of copper and tin. We will discuss this in the next slide. The heterogeneous alloys are those in which the added elements are randomly distributed as islands of added material. The composition may vary significantly with location on the atomic level. Two examples of a heterogeneous alloy are tin and the lead solder, and mercury amalgam, which is used to fill teeth. One example of a homogeneous alloy is bronze, in which the host metal is copper, and may contain up to 30% of added tin. Bronze is an example of substitutional alloy, in which the added metal tin replaces the atoms of a host element copper in the crystal lattice. This is illustrated in this figure, in which the atoms of tin, represented in white, occupy the locations on the face and the corner of the face-centered cubic lattice characteristic of a copper, as you can see over here. Since the tin atoms are slightly larger than the copper atoms, this disturbs the crystal lattice to a slight extent so that the layers of atoms do not slide past each other quite as easily. As a result, the bronze is not as malleable, but it is harder and stronger than the pure copper. An interstitial alloy is a mixture in which atoms of the added element occupy void spaces between host atoms within the crystal lattice. There are three types of void or holes in the unit cell. The first type is the cubic, which is the void within the center of a simple cubic structure, which is not indicated here. The second type is tetrahedral type of void. It's located between the clusters of 4 host atoms. The third type of void is octahedral. This is located between the clusters of 6 host atoms. The last 2 void spaces are typical of closest packing structures. Note that the volume available for each of these types of holes will determine whether or not a given element can easily fit within the void. The size of the atom that will fit in the hole is determined by the ratio of the added atom compared to the host atom. One example of an interstitial alloy is carbon steel, in which the carbon atoms occupy the octahedral holes within the face-centered cubic lattice characteristic of iron at a high temperature. As you can see, carbon is embedded in the octahedral holes. As the iron cools, it converts to a body-centered cubic lattice, and the octahedral holes breaks down. The carbon atoms may either precipitate as clusters or form iron carbide, which disrupts the normal lattice structure of the iron and adds strength to the steel compared to the pure iron. Ionic solids consist of monoatomic and polyatomic ions held together by ionic bonds or electrostatic forces. Most ionic solids are crystalline with unit cells that can be classified using the unit cells we discussed previously for the metals. For example, consider the NaCl. The crystal lattice is face-centered cubic cell of chlorine. So look at the green ones, they are chlorine. The chloride atoms with sodium ions occupying the octahedral holes formed between the chloride ions. Please note that sodium ions are smaller in size than chloride ions. So here's the sodium ions. Chloride, the anions, occupy the corners and the faces of the face-centered cubic unit cell. As discussed previously, the face-centered unit has 8 corners. That's 1 atom from all the partial atoms on the 8 corners, plus the 6 faces times a half, which is 3 atoms from the faces of the cube. So we have a total of 4 chloride ions in the unit cell. For sodium ion, the cations actually occupy the spaces along the edges. That's all the sodium ions are on the edge. Remember, we have a total of 12 edges. So you have 12 edges. Each edge contributes 1/4 of the atom inside the unit cell, plus the sodium ion that is at the center. So we do have a sodium ion at the center, okay? At the center, you see that? A little bit of that. So at the center, look at the center atom over here. It's way inside. We do have another sodium ion inside. So plus that 1 at the center, we also have 4 sodium ions. So as you can see, we have 4 chloride ions forming the face-centered cubic, and we also have 4 sodium ions. So it's the 4 sodium ion and the 4 chloride ion. So you look at the ratio of sodium ion and chloride ion, it's 1-to-1 ratio. So you have the formula as 4-to-4, which is a 1-to-1 ratio for sodium chloride. Another example of an ionic crystalline solid is Sphalerite or zinc sulfide. It exhibits a face-centered structure for the sulfur atoms as represented in yellow here. You have 8 corners, and you also have 6 face sulfide ions. And when you look at zinc ions are in 4 of the 8 tetrahedral holes, as you see over here. So the face-centered sulfides will give you 4 sulfide ions in this unit cell. And all the 4 zinc ions are totally inside the unit cell. So you also have 4 zinc ions. So for this reason, it's 4 versus 4 for ionic compound. You have a ratio of 1 to 1. So zinc sulfide has a formula of ZnS, 1 to 1 ratio. Let's work on one example, which we just analyzed. So Sphalerite zinc sulfide has sulfide ions in the face-centered structure, with zinc ions occupying 4 of the 8 tetrahedral holes in the unit cell. We want to verify that the unit cell is neutral. So as we know, from the lattice unit cell information, we can calculate the number of each ion in the unit cell. For the sulfide, it has the face-centered cubic lattice, have a total of -8 charge for the sulfide. The reason is because we have 4 total sulfides. So the total negative charge is 4 times -2. Each one is -2. So 4 sulfide atoms, that's total of a -8 charge. And for zinc, since all the 4 zinc ions are inside the unit cell, so we have a total 8 positive charges as well, because each zinc carries 2 plus, so 4 zinc ions times +2, that's +8. So for this reason, the total charge of this unit cell is 0. That would be expected for an ionic formula unit. Let's look at another example. For fluorite, calcium fluoride, CaF2, it exhibits a face-centered structure in which the calcium ions form an expanded face-centered structure. The calcium ions are actually not touching each other. At the same time, the fluoride ions, represented in green here, occupies the all 8 tetrahedral holes within the unit cell, as you can see over here. We can verify the charge neutrality. For calcium ions, it forms the face-centered cubic FCC structure, so 4 ions per unit cell. For calcium, it has 4 total ions each unit cell, so it's a total of +8 charges. For the fluoride ion, we have 8 tetrahedral holes. All of them are inside the unit cell. So for 8 fluoride, each fluoride carries 1 negative charge. This means the negative charge and positive charge, they do cancel out. The formula is neutral, which is expected. Now let's talk about allotropes of carbon. Allotropes are different molecular structure of the same element. Allotropes are different molecular structures of the same element. For example, oxygen has allotropes of O2, which is oxygen gas, and O3 as the ozone. Carbon has 3 major common allotropes. The first one, the diamond. Diamond forms a covalent network of sp3 hybridized carbon in the tetrahedral shape, as you can see over here. It forms an extended network in 3-dimensional array. The rigid tetrahedral structure is responsible for the diamond being the hardest naturally occurring material, because they are always connected. Cutting off any place would have to break a host of covalent bond. Diamond can be formed synthetically from other carbon sources, such as graphite, under high temperatures and pressures. The synthetic diamond formed industrially are used as abrasives and coatings for cutting tools, such as saw blades, etc. The most abundant allotrope of carbon is graphite. It's found in soot and smoke, and it's used to make pencil lead, lubricant, and gunpowder. Graphite consists of two-dimensional layers of sp2 hybridized carbon atoms covalently linked in the sheet of fused six-membered carbon rings. As you see how you have sheets of graphite. The delocalized electrons associated with the pi bonds within the carbon rings in the sheet-like structure results in the good electrical conductivity. The weak intermolecular forces between the layers allow them to slide past one another relatively easily, which explains its application as a lubricant and a pencil lead. If a single layer of graphite is isolated and curled back to form a tube, we have another form of carbon called a nanotube. As with the graphite, the delocalized electrons associated with the sp2 hybridized carbon atoms result in good electrical conductivity. The highly covalent structure within the tube results in high mechanical strength, and the carbon nanotubes have been used to strengthen fibers in sports gear. The final allotrope of carbon was discovered in 1980s and consists of clusters of carbon atoms covalently bounded in sp2 hybridized bonds. The 5 or 6 membered carbon rings are arranged to resemble the soccer ball. This allotrope is known as the fullerene. Because of the resemblance of the structure to the geodesic domes designed by the American architect Buckminster Fuller, also known as the buckyballs. Too small to be classified as a covalent network and too large to be molecular solids, so they are classified as so-called clusters. Now let's talk about polymers. A very large molecule with high molar mass formed by bonding together a large number of small molecules of a low molecular weight are so-called polymers. Typically, polymers have masses up to exceeding 1 million grams per mole. Examples include the polyvinyl chloride, or PVC, used to make drain pipes and other building materials, and Teflon, used for non-stick coatings. The smaller molecular weight units that combine to form polymers are known as monomers. In between the smaller monomers and the larger molar mass polymers are mid-sized molecules that are called oligomers. Typically, small organic molecules have well-defined physical properties, for example, melting points, boiling points, etc. The physical properties of polymers depend as much on their molecular weights as on the functional groups that are present. They typically do not have well-defined melting points and usually are too large to enter the vapor phase. Some widely used polymeric alkanes are produced by reaction of short alkenes. The simplest example is polyethylene, or PE. Polyethylene is known as the homopolymer because the macromolecule is prepared by adding the monomers together to grow a polymer chain. So it's ethylene molecules combined together. It's also called the addition polymer because the macromolecule is prepared by adding monomers together to grow a polymer chain. The reaction in which the two reactants are coupled together without the loss of any atoms is called the addition reaction. The key feature for addition reaction is there is no loss of any atoms in the polymerization process. In most products made of polyethylene, a very large number of monomer units are involved. So the N is going to be in between 100 to a million. The properties of the polymer will depend on the value of this N over here. So the N could be very large. It also depends on another factor, which is whether or not the polymer is a straight chain or is branched. So consider the difference between the high density polyethylene, also called HDPE, and the low density polyethylene, also called LDPE. The structures for both types of polymers are shown in this figure. The HDPE is prepared for the long, straight chains of polyethylene, which we can stack neatly in an ordered crystal structure. This efficient packing results in a very dense and rigid polymer. The plastic is used to make milk containers. If very long chains are involved, the product is called the ultra-high molecular weight polyethylene and is used as the coating on some artificial ball and socket joints. In contrast, the branched structure, as you see over here, for the LDPE prevents this efficient stacking and results in a more flexible polymer, such as that used in the plastic shopping bags. Examples of other polymers include Teflon. Teflon is a polymer made from monomers of tetrafluoroethylene. It is also an addition polymer and a homopolymer. Structurally, it's identical to polyethylene except that all the hydrogen atoms have been replaced with the fluorine atoms. It's chemically unreactive and can withstand very high temperatures and has a low coefficient of friction. It's used as the non-stick coating in cookware. Individual aromatic rings as well as fused rings are flat molecules, thus they tend to stack neatly, which gives rise to useful properties. Notice the benzene rings, they are very, very flat over here, and they can stack well with each other. One example of the aromatic polymer is polystyrene. The monomer unit is benzene ring. As you see over here, these are all so-called benzene rings over here. The resulting polymer is called polystyrene, or simply PS. Solid PS is a transparent, colorless, rigid plastic used for compacted disc cases in the plastic cutlery. This form is produced when the rings forming different polymer chains are allowed to stack neatly on each other, as you see over here. They are stacked in a very neat order. If an inert gas, such as pentane, is blown into the molten polymer, it creates spaces in the polymer and prevents the rings from stacking. The result is the polystyrene foam, or styrofoam, used in coffee cups and the styrofoam coolers. The most common polymer contain alcohol and or ether function groups is the polyvinyl alcohol, or PVAL. The OH groups in the PVAL makes the surface very polar, which makes it a good barrier to prevent the penetration of hydrocarbon solvents and the carbon dioxide. So the impermeability of carbon dioxide CO2 makes PVAL useful in the manufacture of soda bottles, which is blended with polyethylene terephthalate, or PETE, to create a layered polymer. The PETE provides rigidity and mechanical strength, while the PVAL creates a barrier to prevent the loss of dissolved CO2 from the soda water. When PETE and PVAL polymer, the PETE and PVAL polymer is a physical mixture of two polymers. The new material can also be made by combining different monomer units. This type of polymer is so-called a copolymer if two different monomer units are involved, and is also called heteropolymer if three or more different monomers units are used. In this case, two different monomer units are used. In contrast, the heteropolymer is made by three or more different monomer units. The esters and amides are related to the carboxylic acid. The presence of a carbonyl group makes the ester polar. You see the carbonyl group, carbonyl group, carbonyl group, carbonyl group. So amide is also polar. Because of this reason, their boiling points are comparable to those of aldehydes and ketones of similar size. The formation of esters and amides from carboxylic acids is the result of so-called condensation reaction. This is an ester, this is the ester functional group, and this is the amide functional group. In this process, a small molecule like water is lost. And this process is so-called a condensation reaction. A small molecule is being lost in that process. The polymers of esters and amides typically have multiple functional groups. For example, here you also see alcohol functional group. Polyamides are also difunctional polymers formed by condensation of the reaction between the amine and the carboxylic acid. This is the amine carboxylic acid. The original monomers used to form the polyamide can be identical with the carboxylic acid functional group on one end and the amine group on the other end. That's the amine group. Probably the most familiar amide polymer is nylon 6,6, made from the adipic acid, a dicarboxylic acid, and the hexamethylene diamine. The nylon polymers forms long, thin fibers which are strong and can be woven into fabric. A special variety of nylon is used to make a Kevlar, a very strong polymer used in the bulletproof vests, puncture-resistant tires, and face masks for hockey goaltenders. Kevlar is formed from the terephthalic acid, which is a dicarboxylic acid, and this is dicarboxylic acid because you have two carboxylic acid functions, and the diaminobenzene, which has two amino functional groups. The strength of the Kevlar is due to the ability of the polymer chains to form the cross links through the hydrogen bonding, and they can stack neatly because of this planar aromatic rings within the polymer chains. So we have talked about the details about the different unit cells, and we also talked about the different types of allotropes. So that's it for today, and have a good day. See you next time.